Have you ever wondered what entropy is and why it's important in physics? Well, you're not alone. This elusive concept has been a vital part of scientific discussions for centuries. So, let's demystify it together. In the realm of physics, entropy is a measure of the disorder or randomness of a system. It's like the degree of messiness in your room. The more scattered your belongings are, the higher the entropy. But how does this connect to physics? This is where thermodynamics comes in. Thermodynamics, a branch of physics, studies energy transfers such as heat and work between physical systems, and entropy plays a central role in it. It's a fundamental quantity that helps us understand how these energy transfers occur. Now, consider a system with low entropy. This system is highly ordered, much like a perfectly stacked deck of cards. In contrast, a system with high entropy is more chaotic, similar to a deck of cards scattered on a table. A common example used to illustrate entropy is the spilling of a glass of water. Initially, the water in the glass is orderly, but when spilled, it spreads out and assumes a more disordered shape. This disarray signifies an increase in the entropy of the system. So in essence, entropy is all about the order and disorder in a system. Now let's delve a little deeper. You might have heard about the second law of thermodynamics, but do you know how it is tied to entropy? Dive in with me as we explore this fascinating law that governs the universe. The second law of thermodynamics is all about entropy. It states that the entropy of an isolated system never decreases over time. Instead, it tends to increase. To put it simply, things get messier as time goes on. But why is this? Well, it's all related to the concept of the irreversibility of natural processes. Think about a movie of a glass shattering. If you play it backwards, it looks odd, right? That's because the process of a glass shattering is irreversible. In the same way, nature has a preferred direction, from order to disorder, from low entropy to high entropy. This law is not just about broken glasses or spilled milk, though. It's about the universe itself. The stars in the sky, the swirling galaxies, even the flow of time, they're all subject to the second law of thermodynamics. As time progresses, the universe becomes more disordered, more chaotic. But don't get the wrong idea. Chaos isn't necessarily a bad thing. In fact, without this increase in entropy, life as we know it wouldn't exist. The energy from the sun wouldn't reach us, plants wouldn't grow, and we wouldn't be here. So in a way, the second law of thermodynamics is essential for life. Entropy is a bit like the cosmic clock of the universe, always ticking forward. It's a fundamental concept in thermodynamics, a branch of physics that studies energy transfer. It's intrinsically linked to heat and temperature, and it's the reason why your coffee gets cold if you leave it sitting around. In essence, the second law of thermodynamics gives us a glimpse into the heart of the universe. It tells us that everything is in a constant state of change, moving from order to disorder, from low entropy to high entropy. And while this might sound a bit melancholic, it's actually quite beautiful. It's the law that gives rise to stars and galaxies, life and death, the endless cycle of the universe. Thus, as time progresses, systems tend to evolve toward states with maximized entropy. Entropy isn't just about disorder, though. It's closely tied to the dispersion of energy. But how? Well, think about a glass of water sitting on a table. The water molecules are neatly contained within the glass, in a relatively ordered state. We can say this system has low entropy. Now, imagine if the glass were to tip over, spilling the water onto the table. The water molecules spread out, covering a larger area and assuming a far less orderly arrangement. In this case, we'd say the system now has high entropy. That's the crux of it. Entropy is all about how energy, like our spilled water, spreads or disperses. When energy is concentrated like the water in the glass, entropy is low. But when that energy spreads out, as in the case of the spilled water, entropy increases. Let's delve a bit deeper. Consider the spilled water again. It didn't just randomly decide to spread out. It was the result of energy, in this case, kinetic energy, being transferred from the tipping glass to the water. This energy caused the water to move and spread out, increasing the system's entropy. Now, what if we could reverse that energy transfer, make the spilled water gather itself back into the glass? Well, that would be a decrease in entropy, which, as we know from the second law of thermodynamics, is a big no-no in an isolated system. In the real world, this process is irreversible. The entropy of the system always tends towards maximization. This is why the concept of entropy is so crucial in thermodynamics, the branch of physics that studies energy transfers. It gives us a way to quantify and understand the natural tendency of energy to disperse and why certain processes are irreversible. So when you spill your glass of water, you are effectively increasing the entropy of the system. It's not just a mess to clean up, it's a fundamental principle of the universe playing out right there on your kitchen table. Now that we have a basic understanding of entropy, let's take a look at the mathematical representation. The formula for entropy is often represented by the letter S and is associated with the change in heat in a system divided by temperature. In mathematical terms, this is expressed as delta S equals delta Q divided by T. But what do these symbols mean? Delta S represents the change in entropy. Entropy, as we've discussed, measures the disorder or randomness of a system. So delta S is simply a measure of how much that disorder or randomness changes. Delta Q, on the other hand, represents the change in heat in the system. This could be heat that is added or removed. Keep in mind that heat is a form of energy, and energy transfer plays a key role in changes to a system's entropy. Finally, T represents the temperature. But not just any temperature, it's the absolute temperature measured in Kelvin. It's important to remember that absolute zero or 0 Kelvin is the point at which all molecular motion stops. So in our formula, T is the temperature above absolute zero. The formula delta S equals delta Q divided by T gives us a mathematical way to calculate changes in entropy. It's a tool that allows us to quantify the degree of disorder or randomness in a system based on the heat change and temperature. This formula is particularly useful for understanding and predicting how systems will behave. For instance, if you know the initial entropy of a system and the amount of heat that will be added or removed, you can calculate the final entropy. This can help you predict the system's final state. In the world of thermodynamics, this formula is a fundamental tool. It's used to analyze everything from the efficiency of engines to the behavior of gases. But its significance extends beyond thermodynamics. It's also used in fields like information theory, where it helps measure the amount of uncertainty or disorder in an information system. This formula, delta S equals delta Q divided by T, is a simple yet powerful representation of entropy. Entropy isn't confined to thermodynamics alone. It finds its applications in several areas of physics. Let's take a deep dive into the world of information theory. Here, entropy measures the amount of uncertainty or disorder in an information system, much like its role in thermodynamics. But what does this mean exactly? Imagine you're trying to predict the outcome of a coin toss. If the coin is fair, you have a 50-50 chance of guessing correctly. This situation is full of uncertainty, and thus has high entropy. On the other hand, if the coin is rigged to always land on heads, there's no uncertainty. You can predict the outcome with certainty every time, hence low entropy. In this context, entropy is a tool that helps us quantify the unpredictability of information content. It's a way of measuring the average amount of surprisal. Yes, that's a real term. It's the sense of surprise you get when an outcome is not what you expected. Another fascinating application of entropy is in the field of cosmology. The cosmic microwave background radiation, this afterglow of the Big Bang, shows a high degree of uniformity. This suggests a high entropy state at the start of the universe. Some cosmologists propose that the universe's ongoing expansion and the formation of complex structures like galaxies and stars are efforts to maximize entropy. Entropy also has applications in statistical mechanics, a branch of physics that uses statistics to explain the behavior of a mechanical system. Here, entropy relates to the number of ways particles can be arranged in a system, which helps us understand phase changes like when ice melts into water. And let's not forget about its application in the realm of black holes. The concept of black hole entropy suggests that a black hole's entropy is proportional to the area of its event horizon. This has been a key insight in the quest to unify quantum mechanics and gravity. Finally, entropy is used in computer science for things like data compression and cryptography. It helps in determining the minimum number of bits required to encode a set of data and in creating keys for secure communication. So while entropy may have started its journey in the realm of heat engines and steam, it has found its way into the heart of modern physics, cosmology, and even computer science. From the toss of a coin to the fate of the universe, entropy is a concept that weaves itself into the fabric of our understanding of the world. So, entropy plays a crucial role in understanding and modeling a variety of physical and natural phenomena.